So the next example that we have is find the area of the portion of the surface f of x and y equal to 1 minus x squared plus y that lies above the triangular region with the vertices that are given here. So the first thing I'd like to do is try to draw that region in the xy plane. Let's say this is 1, minus 1, 1 and minus 1, okay? Each of the vertices of my triangle has z coordinate equal to 0, so of course I know I am in the xy plane. So I'm just going to look at the x and y coordinates. The first vertex is at x equals 1, y equals 0, here. And then at x equals 0 and y equals negative 1. And then at x equals 0 and y equals 1. So my triangle will be this one. So this is the region over which I'll be integrating. And I know that I need to find the first partials. So first partial with respect to x of 1 minus x squared plus y is going to be minus 2x. And the first partial with respect to y will be 1. So square root of 1 plus the first partial with respect to x whole squared plus the first partial with respect to y whole squared. Well, that's going to be equal to, I'm going to get 1 plus 1, so square root of 2, and when I square minus 2x, I get plus 4x squared, or I could write it as 4x squared plus 2. So that's the thing I want to integrate, but I need to figure out how to set up my integral, so I need to know how to describe this triangular region. I think that I want to integrate with respect to y first, and I want to say that y is running from here to here. So I need to know the equations for these straight lines. Because those will be my bounds for y. Well, these are pretty simple. I've got the line of slope negative 1 here, so I think that should be y equals 1 minus x. So my slope is negative 1 and my y-intercept is positive 1. That gives me y equals 1 minus x. And then the other line has positive slope of 1 and y-intercept is minus 1. So this is y is x minus 1. So those will be my bounds for y. And then it looks like I can just let x run from 0 to 1. So let's set up our integration. So I said I wanted to integrate with respect to y first. So out here, 0 to 1 are my bounds for x. My bounds for y are from 1 minus x to x minus 1. And I'm integrating square root of 2 plus 4x squared, first with respect to y, and then with respect to x. So this integration looks like it's going to be a bit more complicated than our first example. So first, let's integrate with respect to y. That's not so bad. Because I just have antiderivative equal to y. Then I want to evaluate it at x minus 1 and 1 minus x, and then integrate with respect to x. So this will be integration 0 to 1, square root of 2 plus 4x, and that's 4x squared here. And then I have x minus 1 minus 1 minus x. And I'll integrate with respect to x. So this becomes integration 0 to 1, square root of 2 plus 4x squared times, I have minus 1, and I have x plus x. So this should become let's see, this should become 2x minus 2 dx. Okay. So it looks like I can split this up into two integrations now. I can say this is integration from 0 to 1 of square root of 2 plus 4x squared times 2x dx. And I'll add integration from 0 to 1, square root of 2 plus 4x squared times negative 2 dx. So the first integration looks like maybe I can do it by just a u substitution. But the second one, I think I'm going to need a trigonometric substitution. So before we start that, let's pull out some constants. From the first integration, I definitely want to pull out 2. But I think I'm also going to pull out square root of 2. So if I pull out square root of 2, that's like dividing by 2 in each place. So I'm still going to have square root of 1 plus 2x squared. And I have x dx. Let's do the same thing in the second place. Let's see what constants we might like to pull out. Since I'm thinking of doing a trigonometric substitution, I want to get rid of this coefficient 4. And I can go ahead and pull out that minus 2. So let's go ahead and make it minus 2 times. I want to pull out square root of 4, which of course is 2. And what does that do inside my square root? Well, it's like dividing by 4 inside my square root. So this is going to become 1/2 plus x squared dx. And just to make it look even a little bit nicer, before I start my trig substitution, let's go ahead and write this as, just make that 4. So 4. Let's write this as 1 over square root of 2 whole squared plus x squared. So it looks like a square plus a square. Okay? So here, I want to let u equals 1 plus 2x squared. Then du is going to be 4x dx. And if I want to change my bounds between x and u, well, x was running from 0 to 1. So that looks like u should go from, if I plug in 0, I get 1, and if I plug in 1, I get 3. So u will go from 1 to 3. So this integration, the first one will become 2 square root of 2. But I need to divide by 4 because I only have x dx. I don't have 4x dx. My bounds will change from 1 to 3 now. And I'm going to have square root of u du, which I like to write as u to the 1/2. Now for the other one, I'll have to do a trigonometric substitution. So I'm going to let x equal 1 over square root of 2 tangent of theta. So then x squared is going to be 1/2 tangent squared theta. 1 over square root of 2 squared is 1/2. So this whole thing is going to become 1/2 plus, by my substitution, 1/2 tangent squared of theta. So that's equal to what I had before in terms of x. My dx is going to be equal to 1 over square root of 2 secant squared theta d theta. And this term, if I factor out the 1 over square root of 2, this should be square root of 1 plus tangent squared theta, which is 1 over square root of 2 times square root of secant squared theta. And I'm going to say that's 1 over square root of 2 times secant of theta. Of course, square root of secant squared should be absolute value of secant, but because we're on the positive side of the x-axis, I know my secant, it should be positive between 0 and 1. Okay, so that's going to be fine. Then this integration, oh, I also need to change my bounds. So if I'm changing my bounds, then by this substitution, x is 1 over square root of 2 tangent theta. So tangent of theta is going to be square root of 2x. If I want theta, I need to do arctangent on both sides. Arctangent of tangent is equal to arctangent of square root of 2x. Now I can find my new bounds. If x was from 0 to 1, well, I plug in 0 here. Arctangent of square root of 2 times 0 is arctangent of 0, which is 0. And when I plug in 1, I get arctangent of square root of 2. I'm just going to leave that. So arctangent of square root of 2 is going to be my upper bound. So the integral becomes integration from 0 to arctangent of square root of 2. I think I had a constant out in front. I did, I had 4. So let's put the 4 here for now, and I'm going to have 1 over square root of 2 times secant of theta. That's what was square root of 1 over square root of 2 squared plus x squared. I'm going to multiply by 1 over square root of 2 secant squared of theta, which was my derivative, d theta. All right. So the first integration here, I have the constant simplifies to square root of 2 over 2. And my antiderivative is 2/3 u to the 3 over 2, and I want to evaluate between 1 and 3. And my second integration, when I multiply 1 over square root of 2 times 1 over square root of 2, I get 1/2. So this constant becomes minus 2 times integration 0 to arctangent of square root of 2. And you can see that I have secant cubed. Secant times secant squared is secant cubed. I'm actually going to leave that as secant times secant squared. because if you're familiar with the antiderivative of secant cubed, we're going to need to do it by integration by parts. All right, so back to my first integration here, square root of 2 over 2. Let's go ahead and multiply the 2/3, so we'll say square root of 2 over 3, because 2 and 2 cancel. And I'm going to have 3 to the power 3 over 2 minus 1 to the power 3 over 2. And that's minus 2 times. Now my integration by parts formula, I'm going to first fix secant, and then multiply by the antiderivative of secant squared rather. Antiderivative of secant squared is tangent. I want to evaluate between 0 and arctangent square root of 2. And then the rest of my integration by parts formula is to subtract. But I already had minus 2, so that's going to be plus 2, integral from 0 to arctangent of square root of 2. My antiderivative of secant squared, tangent, times the derivative of secant, which is secant tangent. All right, so just to simplify this constant here in green a little bit, I'm going to say this is square root of 2 over 3. I'm going to think of the power 3 over 2 as first taking the square root and then cubing it. So that's square root of 3 cubed. Square root of 3 cubed should be 3 times the square root of 3 minus 1. Here, in blue, I have minus 2, secant of arctangent of square root of 2, times tangent of arctangent of square root of 2. I'm going to just let that be square root of 2. And then I would evaluate at the lower limit 0, but tangent of 0 is 0, so that doesn't contribute anything. I have plus 2 times integration 0 to arctangent square root of 2, tangent squared times secant theta d theta. Tangent squared, I want to rewrite in terms of secant. I know that tangent squared plus 1 is secant squared. That means that tangent squared should be secant squared minus 1. So in green here, my 3 and 3 cancel. I get square root of 6 minus square root of 2 over 3. So that was the result of that first part of the integration. And here, I want to evaluate the secant of arctangent of square root of 2. So I'm going to think about a right triangle. If theta is equal to arctangent of square root of 2, then tangent of theta is square root of 2. So let me write that. Theta is equal to arctangent of square root of 2 means that I know that tangent of theta is square root of 2. And now tangent I also know is opposite over adjacent, so I'm going to say square root of 2 over 1. Then use the Pythagorean theorem to get the hypotenuse, square root of 3. So square root of 3 is the hypotenuse. I want to know the secant of this angle theta. Secant is 1 over cosine. So secant 1 over cosine. The cosine is 1 over the square root of 3. So the secant is square root of 3. So this term becomes minus 2 times square root of 3 times square root of 2. And now I need to split this integral up one more time. I'm going to distribute the secant theta over the secant squared theta minus 1. So I'm going to first say this is 2 times 0 to arctangent of square root of 2 secant cubed theta and then minus 2 integral from 0 to arctangent of square root of 2 secant theta d theta. Okay, just a little more room to work here. So these constants are still here. I have square root of 6 minus square root of 2 over 3 minus 2 times square root of 6. This integration I want to leave here for now because this is the repetition of my original integration. So this is a repeated integral. I'm going to evaluate this integration minus 2 integration of secant theta. This is another integration that you would have to do by integration by parts. So I'm just going to write the formula here. Integration natural log of absolute value of secant theta plus tangent of theta. And that thing I want to evaluate between 0 and arctangent of 2, arctangent of square root of 2. And of course I still have the plus 2 times. I'm going to write I if I let this thing equal I. And in fact, if I just take the constant 2 with it, I can just say this is I. So I'm saying that I is 2 times the integration from 0 to arctangent of square root of 2 secant cubed d theta, because that is what I started with here. This was also I. Okay, so what do I have then? Let's branch off for just a second, kind of pause here, and say, so I started with minus I up top, and I found that minus I is equal to minus 2 square root of 6 minus 2 natural log. When I evaluate secant at arctangent, I already know that that's square root of 3. And tangent to arctangent is square root of 2. Those are positive, so I'm dropping my absolute value. Then I need to evaluate at the lower limit 0. Well, tangent of 0 is 0, and secant of 0 is 1. So that becomes natural log of 1, which is just 0. So I don't even need to write it, but I'll write it there so that I remember that I did evaluate, plus I. That means I get to say that minus 2I is minus 2 square root of 6 minus 2 natural log of square root of 3 plus square root of 2, and that's minus 0. So I is equal to square root of 6 plus natural log square root of 3 plus square root of 2. So let's go back to what we were working on, we had, from the first integral, we had square root of 6 minus square root of 2 over 3. And then I need to subtract I. So subtract square root of 6 plus natural log square root of 3 plus square root of 2. So I have square root of 6 and square root of 6 cancel. And I end up with minus square root of 2 over 3 minus natural log square root of 3 plus square root of 2. So let's go back upstairs and look at where we were. So I got a negative integration. And the reason for that is because the way I chose my bounds. So here, when I set up this integration, I could have done it from x minus 1 to 1 minus x. So the integration from x minus 1 to 1 minus x of any function should be the negative of the integration from 1 minus x to x minus 1. So what I wanted to do at the beginning is set up the integration from x minus 1 to 1 minus x. Then it's square root of 2 over 3 plus natural log square root of 3 plus square root of 2. And that is the answer to the problem.